Hello everyone, this is Dr. Sulaiman Khan and you are watching my YouTube channel, The Beauty of Mathematics. In today's lecture, I would like to discuss about the fixed point method. For this, I will discuss about the fixed point theorem, which states that for any function g belongs to the uh, interval, this g should be a continuous function in the interval ab, such that for all x belongs to the interval AB, the values of g of x should also belong to this interval AB. And further, suppose that in addition its derivative exists on this open interval, and there would be a constant k greater than 0 less than 1 exist with this condition that the absolute value of the derivative of the g is less or equal to k for any x we are taking from this open interval AB. So while satisfying this condition by the given function by the function g, then for any number p naught in the interval AB, we will define a sequence Pn is equal to g Pn minus 1 for n greater or equal to 1. So then this sequence must converge to a unique point P in the interval AB. So this is the main theorem for the fixed point method. While in this method we will try different uh, approximation of the function f of x. We will change the function f of x to different shapes. uh, uh, X is equal to g of x, like this one. For example, we are given an example f of x is equal to x cube plus 4x square minus 10 equal to 0. So we have to check that it has a root in the interval 1 2. For this we will we are interested to find the root of this equation. For this, first of all, we will change the problem to a fixed point problem, because this x over here is a fixed point of g, and we will show that this x is the solution for this equation. So over here there are different choices, so we can change these equations to different shapes. For example, x is equal to g1, which is x minus x cube minus 4x square plus 10. This is one form. And bx is equal to g2, 10 by x minus 4x whole square root. This is another form, second one. X is equal to g3, which is equal to 1 by 2, 10 minus x cube whole 1 by 2. This is the third form of this equation. We have changed this equation to this form, and x is equal to g4, which is equal to 10 by 4 plus x power 1 by 2. And the last one is x is equal to g5, which is equal to x minus x cube plus 4x square minus 10 divided by 3 square plus 8x. So these are different approximation of this function, this equation. So now we will check each one while taking some number p naught in this interval, and we will define that whether which one among these options A, B, C, D satisfied all the condition of this theorem, and the sequence we will generate from the different values while putting in these options, and we will get that whether they are converging to some unique point or not. So in the next page we have tried these numerical results for these option. For example, for n is equal to 0, we have taken 1.5 as a p naught, and we have generated a sequence for the option A, and we see that when we put 1.5 in this A option, we can get this value, and then we can generate this sequence, and we see that this sequence is not converging to some specific point, because the values are random. Some are minus, some are plus, some are large, some are small numbers. So we can see that this option is not the good option for the so we will skip this one, and we can come to the B option. When we start from P naught, which is equal to 1.5, we can get this value, and so on. And here, when n is equal to 3, we can get this value, which is a complex number. So we also skip this choice, and we come to the option C, which is on 1.5. We get this results, and we see the values are regular and they are in some certain order, and on 30th position we can get this value, which is approximately the exact which is approximate root of the equation of the function f of x, which is accurate up to 9 digit. Up to 9 digit we have got this one. This is a root, and although the sequence is converging to the exact root of the equation, but it is a little slow. So we check the D part, which is also converging to the exact root with the different options. So this one is also a little better than the option C. So it's the approximate root is this one. So this is also the good choice, but it's not too fast. So we can check the option E. On 1.5 we get this value, and after 3-4 iteration, so we have got the same value over here, and there, while this one is converging so quickly. So the better choice for this option is for this function is, or this equation is, this option E. So this is all about the fixed point iteration method, and so for any example we can define the function g with different options, and then we can get that whether which one is the accurate while using the fixed point theorem. So although it's a little complicated task to do these things numerically by hand, so in next lecture I would like to write a MATLAB code for this method, and then we will verify these results while using that code. So see you next time. Thank you.